Hello, how's everyone doing today? Welcome back to Computer Science 3200. Today we are talking about what's possibly my favorite algorithm. Before I get into that, I just had the spooky intro video up there. It's October, and it is a remarkably beautiful day for the middle of October in Newfoundland. It's actually like hot in my office, which is very, very rare for this time of year. So yeah, just wanted to mention that. It's a really nice day out. So let's get on with this lecture. It may go just a little bit long, but it's going to be worth it because I'm going to give lots of hints for assignment 3. And the last lecture went really short in preparation for this one going long. Someone out there asked, what was the song? That was the Tristram theme from Diablo 1. So that's possibly copyrighted music, but hopefully it doesn't strike anything. If it does, I'll start removing music from the video. All right, so today we are talking about my favorite algorithm of all time, which is the MiniMax algorithm with AlphaBeta pruning, and we'll talk about applying this algorithm to assignment 3. So I'm super excited to actually get to teach this to you. So let's just go ahead with it, shall we? All right, so let's get into the lectures. And as always, I'll be doing lectures and then introducing the assignment code after that. So lecture number 10 might be my favorite lecture of the year because I get to tell you about my favorite algorithm, which is MiniMax. MiniMax search, and then on top of MiniMax, we get to do something called AlphaBeta pruning. And this is our first foray into this sort of multiplayer game universe where now instead of just solving mazes or computing paths, you're actually competing against another AI system. So this should be really interesting. Multiplayer games. So far in this course, we've only really looked at problems with a single agent. And so that's called single agent search. So for example, solving a puzzle or trying to compute a shortest path in an environment. Heuristic search can also be applied to environments or games with multiple agents, or in the case of games, it would be multiple players. And as we talked about before, games can have a number of properties. Multiplayer games can have a number of properties that are similar to single agent environments. So for example, games can be fully versus partially observable. They can be deterministic versus stochastic. They can be dynamic versus static. And they can also have different number of players. So for example, how many players are in the game? You might have to decide, well, okay, I'm making a game or I'm trying to apply an AI to the game. Well, the type of algorithm that I can apply, so for example, some algorithms can be applied to deterministic games, but not stochastic games. And just like that, some algorithms can be applied to games with one player, like a puzzle or a Sudoku or something, but not games with multiple players. So examples of the number of players in games, if we're talking about chess or Go or traditional board games, usually there are 2 players. In baseball, we may be talking about, well, there are 18 players, but maybe there's only 10 players at a time and there's 2 teams, so we can think about different games and different players in different ways. In StarCraft, for example, we might be playing 1 versus 1, 2 versus 2, or actually like a free-for-all where everyone is just trying to survive. In something like poker, we could have 10 different people at the table all trying to win each other's money. So games can have different amounts of players just like they can have other properties as well. What about the payoffs for a game? So we just got done with our sort of introduction to game theory and we talked about payoffs. What does each player hope to achieve in these games? This is also very important, and it also defines what the algorithm is that we're going to be using. So for example, in the prisoner's dilemma, we wanted to maximize our utility or maximize our reward or payoff from that game. In poker, we may just want to maximize our own profits. So we don't care about what happens to anyone else. There's a bunch of people playing. We just want to win money. In chess, it might be a little bit easier. It's just win the game, right? I'm playing against someone else. There's a winner and a loser, so I want to win. There's a concept of a zero-sum game in game theory. And I didn't go into this much because it's not super relevant to the course. But in a zero-sum game, each player's gain or loss is equally balanced by the gain or loss of another player. So in a zero-sum game, so for example, if we're playing 1 versus 1 heads-up poker, if there's no rake from the casino and all that, basically, if in order for me to win money, you have to lose money, right? In order for me to win a game of chess, my opponent has to lose the game of chess. And so this is the concept of a zero-sum game. There is, and in the case of a game where there is a winner and a loser, now there might be draws as well, those are zero-sum games, okay? Typically we would say a win is a 1, a loss is a -1, and a draw would be a 0. And the cool thing about zero-sum games is that zero-sum games, there is guaranteed to be a Nash equilibrium. That's pretty cool. So most traditional board games that, like chess, Go, checkers, all that kind of stuff, usually they are 2-player, zero-sum, alternating move, perfect information, deterministic, and discrete. For the most part, right? You can look at some of these and you can easily come up with games that don't fit this. Like, for example, card games are not perfect information. There's hidden information that you don't know about the opponent's cards or something like that. If you think about something like backgammon or Monopoly, there might be dice, right? And so that makes it stochastic and not deterministic. So we're going to be dealing with algorithms that solve these type of games, okay? The traditional board games with no randomness, no hidden information. And who out there can tell me the name of this computer? This is probably the most famous computer of all time. It's called Deep Blue. And Deep Blue was invented by IBM and a bunch of researchers at IBM and other researchers at various academic institutions. And it was the first computer to beat a world champion at chess. And so that was a really big moment in sort of the history of AI. It was by far the biggest headline that artificial intelligence had ever made in the world up to that point, was that a computer had finally beaten the world champion at chess, and that was Garry Kasparov, I believe in 1997. So how could we design something like Deep Blue? Excuse me. How could we design an algorithm to play a 2-player alternating move game? Well, there's a bunch of different things that we could think about. And maybe we'll go in like different levels of complexity. So let's just think about different ways that we could possibly implement an AI for a game like this. So the first one, we might say something like, okay, as a chess player or as a checkers player, as a Go player, maybe I've done some analysis of the game. I've read a bunch of books. Excuse me. I know some basic strategy. I know some tactics, and what I'm going to do is I'm going to try and turn my knowledge of the game into like a program that plays the game. So for example, maybe I want to take pieces that are near the center of the board, or I'm going to like add up the value of the pieces on the board, and if I have more pieces, then I'm winning the game or something like that. So some basic analysis. It turns out that this is what players tried to do at the very beginning, like back in the 50s, 60s, 70s, before there was a lot of computation. And while it did produce a system that could play the game, this couldn't get anywhere near the strength of the best players in the game. So what about thousands of if-then statements, right? Maybe this is the next possibility. We've identified a number of key positions that you could be in when you're playing this sort of game. And you say, okay, if you're in this situation, do this move. If you're in this situation, do this other move. If you're in this other situation, do this other move. And what happens is, as we'll see, there are far too many situations in interesting games to allow that to be possible. Now, that doesn't mean that you can't make an AI that has a bunch of if statements in it. Like, for example, a lot of very early video game AI was just if-then statements. If Mario is over here, walk toward Mario. That is a very fine AI for that purpose. But if we're talking about, sort of hardcore, be the best possible solution for AI, then usually if-then statements do not cut it. Let's try a new idea called, I'm going to call this, let's try some stuff, right? So we'll try some actions, and then we'll evaluate those actions. So what we'll do is we'll say, okay, here's the different things that I'm capable of doing right now in this game. how about I try those things and see where I end up? Okay? So this is what this looks like. If I'm at a current state of the game, I'm going to generate a list of actions from that given state of the game. Then I'm going to evaluate those actions based on the features of the resulting state. And then I'm going to do the action which has the highest evaluation. So let's say I'm at this current state and I'm going to say, okay, I'm going to try action 1, I'm going to try action 2, I'm going to try action 3. I'm going to move my queen to here, I'm going to move my pawn to here, I'm going to move my bishop to here. And then I'm going to look at what would have happened if I had done that stuff, and then say, which of those do I think was the best? Okay, so here's a function that we could use to implement that. So here's my look ahead and evaluate function. So here's my look ahead and evaluate. I pass this in a state, right? So I'm going to be taking the maximum of something. So in order to do that, I'm going to record my current maximum value. And you typically do that by setting that equal to like minus infinity, right? And so I'm going to be taking the best thing, the highest valued thing that I find. Then I'm going to record the best action that I found at some point. So here's the main loop. I'm going to look at my state, and I'm going to get all the legal actions that I can do from that state. So for each action in the legal actions, I'm going to create a new state, which is the child state, and I'm going to say, hey, state, do the action that I'm currently looking at, and create a new state called child. Then I'm going to have some function which evaluates that child state and come up with a value, right? So this might be 10, it might be 1,000,000, might be whatever. If that value is a new best value, then I'm going to record that new best value and mark this action as the best action that I've seen so far. And then what's going to happen is we're going to evaluate the next action and the next action and the next action. And then I'm going to return the best action. So here's an illustrated example of that. Let's say we're playing tic-tac-toe. Now I'm right here in this stage of the game and it's my turn to place an X. Okay? So I'm going to try all of my available actions. And my available actions are, I can put an X here, up on top, I can put an X in the middle, I can put an X to the right. So I'm going to try all those actions and create some child states. So if I put the X in the middle, I get this state right here. Now I'm going to evaluate that state. And I'm going to say, oh wow, I've actually won the game at that state. So that is going to get my maximum possible evaluation. Either 1, if I'm scaling from 0 to 1, it's going to be a 1. If it's scaled from 0 to infinity, I'm going to get infinity. The best thing I can do in tic-tac-toe is win the game, right? So that's a really good evaluation. Now, if I look at this state, well, I haven't won the game, but I also haven't lost the game. So maybe this gets like a 0, right? Because I haven't fully evaluated everything, but nothing bad or good has happened yet. Similarly, if I put my X over here, well, it's the same kind of situation as right here. I haven't won, I haven't lost. So, there you go. Now, so what I would do is I would return this action right here. But, as you can see, this is a flawed way of doing things. I'm only looking one move ahead, right? And as I'm sure you're saying out there, this is a really, really bad move because my opponent is going to be guaranteed to be able to win by placing a 0 or an O in the middle on the next one. But this example that we just did, all it does, that function, is look one move ahead. Okay? So you can see now that we're probably going to want to do something a little bit more complex than this. So, how about we search the entire game tree? So for example, could I look at everything that I could do, then everything the opponent could do, then everything I could do, and sort of this like me, you, me, you, me, you? Could I do something like that? Well, let's have a look. And we've already kind of answered this question in the game. And it turns out that the game tree is just really big. So we have some number of actions possible at each state, that's called the branching factor, and the game is going to end after some number of moves. And so the size of the game tree is b, the branching factor, to the power of the depth, right? And so state and action spaces, So the state space and the action space, which we already talked about, the state space is the number of possible configurations of an environment there are. The action space is the number of actions that are possible from a state. And so we estimate the complexity of the game through these values. And so the way we compute these things is essentially by taking, and we've done this already, so I'm not going to go in depth with the calculation, but it's by taking, if we have a board like chess or checkers or whatever, we take the number of possible pieces that could be at each state, and we take that to the power of the number of board states that there are. And so we can see that for tic-tac-toe, there might be 10,000, right? For chess, there ends up being a lot more than 10,000. This number is very, very big. I'll just let the animation play out. And so what we end up with in the end is 10 to the 42 or 10 to the 43 possible chess positions. And when we have a game like Go, it ends up being even bigger. So I won't play the whole animation now. But what we see here is we asked the question, could we just search all of the moves for the entire game, right? So if we want to answer that question, we should figure out how many moves there are. So for tic-tac-toe, this is just the number of possible states that there are in a game. And as I said, as we talked about before when we did this analysis the first time, there are actually far more game tree. The space of the game tree is higher than the state space. So the state space, again, this is a good exam question. The state space is the number of board configurations. The game tree space is the number of possible games that could be played, right? So the number of different sequences of moves that there are possible. So for example, of the 10 to the 43 possible chess states, there are way more game trees because there are millions, if not billions or trillions of possible ways to get to every possible chess state, right? So this value here measures if we wanted to search the entire game tree, how many operations would we have to do? And 100,000 or 10,000 for tic-tac-toe, that's fine. For tic-tac-toe, we could feasibly, in like a millisecond, search all of the possible states of tic-tac-toe. But as soon as we get into bigger games, we cannot even think of searching the entire game tree. So we said, okay, let's try to look ahead one depth, right? That didn't work because we want to analyze more things, but we can't search the entire game tree. So I think the natural place to fall is somewhere in the middle, which is let's look ahead as far as we can. And what does as far as we can mean? Well, it means whatever our resources are capable of doing. So we may say, okay, maybe I can search a total of like depth 2 or 100,000 nodes, or I'll search for an hour, or whatever our time or memory constraint is. That's how far I will look ahead. And hopefully this will give us enough information to make a decent decision. Now, when you have competing players, so before when we looked at the search tree for a single agent search, every node was connected by edges, right? So we have nodes that are connected by edges. When it was a single agent problem, every edge was the action that, for example, with pathfinding, took you from the state of this node to the state of another node. Every action in a single agent search belongs to the same agent, right? It belongs to the only player of the game. When we're talking about now having two players in a game, and those players are competing, and again, this only applies to alternating move games, we have one player doing one set of actions, and another player doing another set of actions. And so at some particular depth, the nodes will specify, okay, all of these nodes, these are player one's moves, and these nodes, this is where player two can move. Okay, so if we have a node with a node here in the game tree with a corresponding color, I'm just color coding these. This might be player one, and this might be player two. At some point, we're going to reach the limit of our search, right? Either we've run out of time, or we've set a depth limit, or we've run out of memory, or something like that is going to happen where we have to say, okay, we haven't searched the entire game tree because that's too big, but I have to stop here. I just have to stop. Something is telling me to stop. And what I'm going to do at that point is the leaf nodes of this search, I am going to apply an evaluation function to that search. And that evaluation function, or to those states. And that evaluation function typically is going to say something like, I want to be in that state this much. It's this good for me to end up in that state. So ideally, what I want to be able to do is take the actions that will lead me to that state. But what you have is, you can't just go straight to the state that you want to do, because there's another player trying to do the opposite of that. So let's have a look. If you have player 1, so let's say that the root node of this game tree, I'm currently playing chess, for example, and I have the white pieces, right? So I'm going to go first. So player 1. Then player 2 has the black pieces. They're going to go after me. What I'm going to say is, okay, after I've moved, and then after the other player has moved, maybe my limit was a depth 2 search for whatever reason. So after player 2, the other player has made their moves, I'm going to end up with some evaluation. I'd love to end up here because an 8 to me is the best of all of these states, right? So over here I have a 2, that was like kind of a bad state. I don't really want to be there. Oh, a 6, that's pretty good. I'd like to be there. A 1 is here, that's really bad. An 8 is here, that's really good. So ideally, I'd like to end up in these states. But there's another player who's able to take actions, right? And I'm trying to maximize my outcome, but they are trying to minimize my outcome. All right? So when we take a tree to look like this, instead of saying player 1 and player 2, it makes sense to frame it like this. The player who's trying to maximize the values and the player who's trying to minimize the values. Okay? So, again, think of a game of chess. I've got a number of possible moves that I can do, and the opponent is going to have a number of possible moves that they can do after that move. We've looked at all of those possible scenarios. So if I have these 2 actions, and then after those 2 actions, my opponent has 2 actions. Now for a game of chess, it would probably be like 50 actions or something. But we've gotten to this level where we have applied some evaluation function. And we've said, okay, I prefer to be in either this state or this state. But it's before these states, it was actually the opponent's choice of move. And the opponent is going to look at these evaluations and say, I want to minimize those values. So if the minimizing player is currently deciding, and it says, oh, look, I could either go to this state where there's a 2 or this state where there's a 6, well, that's my opponent, and they're going to choose to go to the 2 state, right? Because they want to minimize the best thing that I could possibly do. If instead my opponent was over at this node, they would look ahead and say, oh, this state leads to a 1 evaluation, this state leads to an 8 evaluation. So my rational opponent would choose the action that leads to the 1, right? So now, because the opponent was minimizing, and they could have either gone to this state or this state, then I'm going to have to maximize over these values, right? So it's saying, okay, my opponent has put me in one of these situations where they tried to minimize my result, but now I have a choice of the 2 things that they could give me, and I'm going to try and maximize that result, right? So of the 2 and the 1, I'm going to choose to go here because it's the best worst case scenario, essentially, okay? So I hope you see how that works. The player whose current turn it is the maximizing player. They are trying to get to the best evaluation state. But between me and the other player, there's a minimizing player trying to minimize my outcome. So we are competing in that respect. They want the lowest possible outcome for me, and I want the highest possible outcome for me. All right. So that's how that works. So as we saw before, this is this look ahead and evaluate function. Okay, let's try and put what we just did into an algorithm. So what we just did was we said, okay, I'm trying to maximize something, right? But I'm trying to maximize the result of a minimize from the opponent. So at some point, we're going to have a minimizing function and we're going to have a maximizing function. Okay, so here's what that will look like. Here is a single depth maximizing function. So we have a MaxValue function which takes in a state. We have this value, I'm going to just call it v for value. It's going to be set to -infinity because we're trying to find the maximum of something. So for each child in the children of S, that just means, for each action we would create the new child. I'm just sort of taking a shortcut here. For each child in the children of S, we're going to record the evaluation of that child. And if that evaluation is greater than my current maximum, I'm going to record it. And then what I do is I'm going to return the best value that I could have gotten. Right? See how that works? So what I'm doing here is essentially down here, but the maximizing version of that. Find the maximum value of everything one depth ahead of me. However, that's just for a single depth. If I want to look at that in terms of the full tree, right? So that was just this layer. But as you can see, the maximizing player wants to maximize the values of the minimizing player. And if we were to, have more depth in this tree, the minimizing player would be in turn minimizing the result of a maximizing player, who would be maximizing the result of a minimizing player. So we go max, min. Oh, maybe now you can see where the name of this algorithm comes from, the MiniMax algorithm. So that's a bit of a spoiler, okay? So the full tree would look something like this. If we are at a terminal state, and again, the terminal state is wherever we had to stop. So a terminal state might be where we reached a depth limit, we reached a timeout, or maybe the game was actually over at that state. Maybe we had won. So there is going to be something that tells us that this is a terminal state, meaning we should stop the search at that time. So if it's a terminal state, that is where I do the evaluation. Otherwise, I'm going to be maximizing. So I'm going to I'm going to set up a -infinity for each child. Instead of just evaluating here, I want to maximize the result of a minimize, right? And so I'm going to get the value of that eventually and then compare it to my maximum, and I'm going to return that. However, there's a MinValue algorithm here, which is just the exact opposite of this, right? So we've got MaxValue and MinValue, and this is what would happen on the full tree. So MinValue over here is the exact same thing as MaxValue, except instead, it is trying to find the minimum of something, so this v gets set up to +infinity, and we're checking to see if it's less than that instead of greater than that. So look at this. We'll look at it one more time. MaxValue says, if the state is terminal, return the evaluation. Otherwise, take the maximum of all the MinValue calls. And MinValue is saying, if the state is terminal, return the evaluation. Otherwise, take the maximum of the MaxValue calls. So let's look over here. And it says, okay, we're currently the maximizing player, right? So if this is a terminal node, evaluate it. It's not a terminal node. So I take the min player algorithm. Now the min player algorithm gets applied here, and it says, is this a terminal node? It is now. So apply the evaluation function and take the minimum of all of those. And that's what happens here. Now, the maximizing player looks at its next action and says, is this a terminal node? It's not. And so the min player's algorithm happens, and then it applies that same logic to these two and sees that they are terminal nodes, so it returns the evaluation. And then once we have values here, then the max player is now free to actually maximize those values. So that's what this algorithm is doing. There's a maximizing part and a minimizing part, and they alternate at different depths of the tree, and those alternating maxes and mins correspond to me, the maximizing player, taking my turn, and you, my opponent, the minimizing player, taking your turn. Now, this again is for the full tree, right? And so we cannot do the full tree. So what we typically do is we apply a depth limit. And that depth limit we're going to apply, there's no changes to the algorithm. What we're just saying here is that that terminal, instead of the state just being terminal, now we could be at a maximum depth. So before I said that terminal S, okay, we could be at a maximum depth. Terminal S here just means that the game would be over there. Or are we at a maximum depth? Okay, so those are the two ways that we could stop this process from infinitely recursing. Either the state is terminal, meaning that it's the end of the game, or some depth limit, maybe we have a depth limit of 2 here, that depth limit has been reached. All right? So we just add a depth limit in here. And then the only other thing that we have to add instead of this if statement is that when we then call the MinValue function, we have to pass in depth plus 1, right? Because here, we're at depth 0, here we're at depth 1, here we're at depth 2, here we're at depth 3. So we just, whenever we call that function, we have to call the next depth so that we can actually record that function. Now, this is all well and good. We have a maximizing function and a minimizing function. However, we want to put that into one function because it would be nice if our algorithm was a single function. So we have a min function, a max function. It mins, it maxes, it mins, it maxes. How about this algorithm is called the MiniMax algorithm? So this is what we've done. If we look here, this lines 2 and 3 of these two functions are identical, right? It just says if we should stop, evaluate the state. Otherwise, if we're maximizing, try and get the max. If we're minimizing, try and get the min. So what we can do to create a single function is just take this part and put it in an if statement. And that's what we've done. So we've got one other parameter here now, because here in the max function, we knew we were maximizing. In the min function, we knew we were minimizing. So the extra parameter here called max is just a Boolean which says, is this iteration of this function, should this be a maximizing step or a minimizing step? So I've got those same two lines up here that just says, okay, if we should stop, return the evaluation. Otherwise, if we're maximizing, maximize the value. Otherwise, we're going to be minimizing, so minimize the value. And we see here, the only other difference is that if we are maximizing, the next call, this is a recursive function, it's calling itself. So the next recursive call to this function, if we are maximizing, should be minimizing. So if we're maximizing, we pass false into the next call, so that we'll go to this branch. And if we're minimizing, we pass true, so that we'll go to this branch. See how that works? So we've taken the max function and the min function and just squeezed them together into a single function that both maximizes if I have to maximize or minimizes if I have to minimize. And that's it. That is the MiniMax function. And I know it's pretty simple, but it's very, very powerful. Now, here's a very interesting form of the MiniMax function or the MiniMax algorithm. It's called the Megamax algorithm. And it's the exact same algorithm as MiniMax. It will produce the exact same result as MiniMax. However, because algorithm creators are super nerds and us people who do algorithm analysis and writing algorithms, we want things to be just as compact as possible. So what some person figured out a long time ago was that the max of A and B is equivalent to the negative max of negative A and negative B. So you can use that fact to get rid of the if statement, essentially. So we have the same two lines up here, and here we only have a single check, and it's saying that we're going to take the maximum of the negative result of negamax. And that works out because the maximum of A and B is equal to the negative maximum of negative A and negative B. So Please don't implement Megamax on your assignment. I just wanted to show you this because if you look up MiniMax online, and I'm sure you will, you might get this version of the algorithm. And you might say, what the hell? Why doesn't it have this if statement? Well, here's the reason for that. But trust me when I tell you, this version of the algorithm, even though it's a little bit cleaner, it is way harder to understand conceptually, and it is way harder to debug practically, okay? Because you don't know when your error is occurring, if you're maximizing or if you're minimizing. It's a bit of a nightmare. So while it is, in theory, the exact same algorithm, in practice, I don't recommend implementing it. Let's look at the properties of the MiniMax algorithm now that we have shown the MiniMax algorithm. MiniMax is complete and it is optimal. It will find the optimal solution up to a given depth, right? So if you have said, hey, search the whole tree, if we have infinite computation time, it will find the best possible answer. And each player plays a best response to the possible actions of the other player. Look at this. Isn't this really cool? So the minimizing player is choosing the best thing for them. And then once it chooses all of its options, the maximizing player is choosing the best thing of all of these. So at each depth, it's a series of best responses. And from our last lecture, what happens if we play best responses? What is the definition of when everybody is playing a best response to everybody else? What did we call that? All right. Well, we called it the Nash equilibrium. So, if for two-player, okay, let me say one more thing. If we can search the entire tree, which typically we can't, MiniMax will play a Nash equilibrium. So it will play the strongest possible move if we can search the whole tree. If it doesn't search the whole tree, then what we say as algorithm people is that MiniMax approximates the Nash equilibrium to a given depth, okay? So it looks for all these best responses and does the best that it can, given that it can't search the entire tree. So we talked about Nash equilibrium last time. There's a really cool thing. For two-player, finite, zero-sum games, a Nash equilibrium exists. And recall, each player is best responding to each other in a Nash equilibrium. Neither player can gain by deviating, and neither player has any regrets. So playing a Nash equilibrium is a very strong strategy. Cool. That's MiniMax. MiniMax will approximate the Nash equilibrium. We've already shown that playing the Nash equilibrium is something you probably want to do. Therefore, MiniMax is going to give you a very good move. However, can we improve MiniMax? Can we? MiniMax is already a great algorithm. Can we do better? And the answer is a resounding, oh yeah, we can do better. And it's really cool. Let's look at this example, okay? Here we had this example before. We have a maximizing player, we have a minimizing player, and then we hit the evaluation node. So the minimizing player is going to be looking at these nodes and trying to minimize them. The first thing it says is, oh, so this node, the first child, that's a 2. So what can I think about now as a rational algorithm? So I actually know for a fact that the result of this node, what can I say about it? Just take a second to think about it. Pause the video and think. All right, you're back from the pause, right? The cool thing that we can say already is because this person is trying to minimize all of these nodes, that the result of this is going to be at most 2. It's going to be less than or equal to 2 because we're trying to minimize and we've already seen a 2, right? So now let's say we see a 7 over here, whatever. So the value of this is 2. Now, what do I know about this one? Well, this player is trying to maximize the results of these. And we already know what this player has chosen. So we know now that this value is going to be greater or equal to 2. Okay, so we know that that's going to be greater than or equal to 2 because I already have a 2 to choose from and I'm maximizing. So if this value ends up being less than 2, I don't care about it. So this player then looks at this node. It's not a terminal node, so min takes over. And now min looks down here and says, oh, this is a 1. So what do I now know as the minimizing player? Well, I know that this is going to be less than or equal to 1. No matter what this is, if it's greater than 1, I'm not going to choose it because I'm the minimizing player. So just look at this now. This is a very important point that I want you to not progress with the lecture until you understand the point that I'm about to make. Since the maximizing player knows that its value is going to be at least 2, and this value is going to be at most 1, then no matter what this is, it's going to be less than 2, because this is going to be less than 1, and so I can just say screw it. I don't need to evaluate any of these nodes, because no matter what we end up coming up with here, if it's a 1 million, we will never be able to get here as the maximizing player because the minimizing player will choose this. Okay? So if they're going to choose this, then this ends up, this is going to be less than or equal to 1. So it's not going to be chosen over this one. So I can just say, hey, stop all computation after this node, for this particular node, right? So I don't need to look at anything else because this could be, like, if it's a -5, it doesn't matter because this has to be bigger than 2 for it to matter for this computation. So I'm pruning part of the tree, okay? When you go out and you prune an actual tree, that's what you're doing. So I know here that this is going to be a 2, right? Without ever looking at the computation of this. There could be a million nodes down here and it doesn't matter. This is called AlphaBeta pruning. So, AlphaBeta pruning is not a different algorithm than MiniMax. Sometimes you'll see online someone says this is the AlphaBeta algorithm, right? It's a bit of a misnomer. If I'm being really pedantic, which computer scientists, that's what we're known for, is being pedantic, there's really not an AlphaBeta algorithm. It's technically MiniMax algorithm with AlphaBeta pruning. But you will see almost everywhere people call it the AlphaBeta algorithm, and that's fine, okay? But just realize that it's really not its own algorithm. It's an optimization to the MiniMax algorithm. And the cool thing is it maintains all of the properties of MiniMax, but it's actually better because it cuts off a bunch of branches of the search tree and can yield exponential savings. So it does the exact same. If we do this cut, if we do this in the proper way and make these sort of observations that, okay, this is less than or equal to 1, this has to be greater than or equal to 2, so I can stop. In practice, the really cool thing is it usually results in exponential savings. And I've read a result out there somewhere that if your tree has n nodes in it, and you apply MiniMax, you'll have to evaluate n nodes. But if you apply AlphaBeta pruning, on average, you'll have to evaluate approximately the square root of n nodes. So that's crazy. Like going from n to square root of n in terms of efficiency is a huge speed up. And so this is why it's called AlphaBeta pruning. You take a tree with a bunch of branches that you don't actually need, and you only pay attention to the stuff you do need, right? That is what AlphaBeta is doing. So AlphaBeta pruning is going to be applied to the MiniMax algorithm. And the way we're going to do it is to introduce 2 new variables. Who can guess what those 2 new variables are going to be called? Right? Alpha. So alpha is the best alternative for max on this particular path through the tree. Okay? So alpha was that greater than or equal to 2 that we were looking at. Beta is the best alternative for min on this particular path through the tree. And so if you want to try and this is very hard to visualize, especially when you start getting really deep cuts in AlphaBeta. But the way I look at it is that at some point in the algorithm, you're going to have, okay, my maximizing player knows that I have to be greater than or equal to this thing. My minimizing player knows that I have to be less than or equal to this thing. And so it's kind of a window. And if we see values outside of that window, we can just ignore them. And so we're narrowing and narrowing our search and becoming more and more efficient as we carry on with AlphaBeta search. Okay, so we recall before, this is the MiniMax algorithm when we split it into MaxValue and MinValue. Now let's look at MaxValue and MinValue if we introduce the alpha parameter and the beta parameter. So you can see here that this was MaxValue and MinValue, and all we're doing is adding 2 lines of code and a couple of variables. So it's not that big of a difference, okay? So this is what we're doing. Let me tab back and forth to just show you how little of a difference it actually is. And what's happening here is that we're going to say, we're introducing alpha and beta as parameters to the function. And down here, we're going to do 2 extra checks that says if v prime is greater than or equal to beta, return v. This is for the maximizer. If v prime is greater than alpha, then alpha is equal to v prime. And so this line is the cut, saying that if we see something outside of our window, stop doing computation and just return the value. This line right here says if we see a new best value, then set that equal to alpha. Okay? And the opposite happens over here for the min value. Now, I'm going to give you a very well illustrated example that hopefully it really helped me understand the AlphaBeta algorithm, and hopefully it will help you understand the AlphaBeta algorithm. And a really important note for the AlphaBeta algorithm is that all of these values are passed by value, okay? Not passed by reference. So that matters for the implementation, is that the state, the alpha, the beta, and the depth, you are passing that by value, meaning you are passing copies of those variables. So those variables will propagate downwards in the tree, but they do not propagate upwards in the tree. And I'll show you what that means with this very well illustrated example. Okay, so here's a sample tree that's going to go to depth 4 that has a bunch of values down here. Those are my leaf nodes. That's the terminal nodes with those evaluations. And we're going to apply the MiniMax algorithm with AlphaBeta pruning to this tree. So we're going to apply max value to the starting state. Alpha initially gets -infinity because it's trying to store maxes. Beta gets +infinity because it's trying to store mins. And the depth at the top of the tree is 0. So that's how we call this. Now, so here is... what's going on here? Okay. Here is what's going to happen. The min value and max value algorithms are going to be called. So at the top of the tree, blue is max value, min is min value. So I essentially keep going down until I get to a root node, right? Or until I get to a terminal node. Because this just says, okay, if it's not a terminal node, go down and switch from max to min. Then min will say, if it's not a terminal node, go down and switch from min to max. So I don't really do much until I get to an evaluation node. However, so let's just do this. Okay, so my value here, I have, if you see a negative here, it means -infinity. So here, my v is -infinity. That is my current best value. My alpha is -infinity because that's what I passed it in as. Beta is +infinity, which is right here. So v, -infinity, alpha, -infinity, beta, +infinity. Now, down here, I'm going to be keep track. So I don't have an evaluation node, so I can't do anything yet. So max calls min, and so I go down in the tree. Min here is trying to store a negative. So as you see in the algorithm, this v for the min value is +infinity. So that's why this is positive infinity here. Alpha and beta get passed down. Alpha is still negative infinity from this call of the function. Beta is still positive infinity. Well, we still don't have an evaluation node, so now min calls max. And now again, max calls min. But now I am at an evaluation node down here. Okay? So here, for your viewing pleasure, is the MinValue algorithm. It's going to look at these and do the following. So here's my v prime, 8. My v is currently positive infinity. My alpha is negative infinity. My beta is positive infinity. Here's what the algorithm says. If the new value is less than the old value, then set it as the old value. Okay? So that's what I'm doing. I'm going to set that. So now, I'm doing all three. If the new value is less than or equal to alpha, then just return the value immediately. Well, alpha is negative infinity, so this is not going to be less than negative infinity. So I'm not going to do this pruning step. The other step says if v prime is less than beta, then beta is equal to v prime. So that is true. So I'm going to set beta to v prime. So here what I've done is I've set v equal to v prime, which is 8, and beta equal to v prime, which is 8. Now we're going to look at the next one, right? So the next one is going to say, okay, is 7 less than v, which is 8? Yes, it is. So I'm going to set that. Is it less than or equal to alpha, which is minus infinity? No, it's not. So I'm not going to be returning the value. If v prime is less than beta, beta equals v prime. So after looking at that, I can say, okay, yes, I did set a new value because 7 was less than 8, which was v, and 7 was less than beta as well. So now I have finished this particular node's minimizing step. So now I look at this maximizing step, right? Because the maximizer is trying to minimize over these things. So this step says, now we're trying to maximize, so we're doing greater than. Look at this value. If that's our new v prime, if that's greater than v, then v equals v prime. So is it greater than minus infinity? Yes, it is. Okay. Is it greater than or equal to beta? Beta is positive infinity. No, it's not. Is it greater than or equal, or is it greater than an alpha? Well, alpha is currently negative infinity, so yes, it is, right? So that's what we set. This is the result of applying this with 7 to our current values. And now we look here. This is so we have this as our current step. We currently do not have a terminal node, so we call minimizing. But look, this is our first example of where our value of alpha now is no longer positive infinity. Right? So alpha value gets passed down. So what this means is through the part of the tree that we have looked at so far, this person up here, this node is a maximizing node, and it knows that its value is going to be greater than or equal to 7. Right? So keep that in mind. That's what the alpha means. Alpha is the top end. Like it's going to be at least that. Well, actually, it's the bottom end. It's going to be at least that much. So now we get to a terminal node and we're looking at the min value. So it says, is this value, v prime, which is 3, is that less than v? Well, v was positive infinity, so yes. And so we're going to set this v equal to 3. Is v prime less than or equal to alpha? If so, just return v. So look at this. 3 is less than alpha, which is 7. So what this means is, essentially, at some point higher in the tree, namely right here, this node knows that the value it's going to get is going to be at least 7. But we're currently minimizing with a 3, so I know that the value that gets going to get propagated upward is going to be at most 3. So that's not going to be at most 7. So it doesn't matter what this value is. I can just stop my computation right here and return the value of 3. Now, this node finishes its maximizing. We know that this is not going to affect it. And so these are the values that we are left with when this is finished. And so the value of that node in the tree is 7. Now, if the value of this node is 7, the minimizer is looking at that value and it's going to set its values. So is it less than or equal to positive infinity? Yes, it is. Is it less than negative infinity? No, it's not. Is it less than beta? Yes, it is. So we're going to set those values to 7. Now we go down through the tree again, we go down through the tree again, but we look now that we have a beta value that we are carrying down through the tree, right? So this beta value is going to be that minimum value. So it's the opposite of an alpha cut. It's a beta cut. So we look here and we say, okay, these are our current values. Is v prime less than v? Well, yes, it is. Is it less than or equal to alpha? Alpha's negative infinity here, so no, it's not. Is it less than or equal to beta? No, it's actually not. So this is the first time where we haven't found a new minimum. So when we finish looking at this node, we have v equal 9, beta equals 7, alpha still negative infinity. Now we look at this one over here. I won't go through all those steps again, but essentially it's not a new beta, but it is a new value. So we set that value. And now we know the value of this node is an 8. Okay? So now we go through the maximizing step because we've seen this value. Is it a new v? Yes, it is, because it's greater than negative infinity. Is it greater than or equal to beta? Oh, look, it actually is. Right? So what's this doing? Well, up here, this is really interesting. So it's the opposite of the last time we pruned a node. This node knows that this is going to be, because it's minimizing and it has a current value of 7, that in order for something to be better, it has to be it has to be less than 7. But this is a maximizing node that's going to be at least 8. So because if this is going to be at least 8, but this one wants less than 7, nothing we do down here is going to matter. So I can prune the computation of that entire part of the tree, return that 8, and then this node does its update step and finds that this is not a new best value, and so this node now gets the value of 7. Okay, hopefully you're following along. I know it's a little bit complicated at first, but just alpha is saying that things have got to be bigger than this, and beta is saying things have got to be smaller than this, right? All right, so up here, now I'm back at the root node, and the root node now has a value. So I can set my value of v, and I can set my value of alpha. Beta doesn't change. Now I go down, so I've got a v value, I've got an alpha value, I've got a beta value. Well, beta is still positive infinity. So I pass these down through the tree, right? Until I get to another evaluation. So let's have a look at what happens all the way down here now. So v prime is 1. Is v prime equal to, is v prime less than v? Yes, it is, because that's currently positive infinity. Is it less than equal to alpha? Oh, it is. So I can prune this one, because this one knows it has to be at least 7, but this one's going to be at most 1. So I can immediately I can stop computing this node and just say, okay, the value of this one is 1. I don't need to go higher than that because this person is trying to maximize with a 7, so no matter what I do down here, it's not going to matter. Now, this one gets a value of 1. Its alpha value is still 7, so it's going to look down the tree. We keep going. This one says, okay, is it a new value of v? Yes, it is. Is it less than or equal to alpha? It is again. So I can do another alpha cut right here. This one is 6. Is 6 greater than 1? Yes, it is. Okay, so I've finished this computation with these two cuts. Now, this node up here has a 6. But watch this. This is where we start to get into the huge amount of savings with AlphaBeta. And I'm lucky to be able to fit this on one slide. This one up here, the root node, knows it's trying to maximize. and it already has a value of 7, right? So this one is trying to minimize, and it already has a value of 6. So this value is going to be less than or equal to 6 no matter what else is computed, right? Because it's minimizing over 6 and a bunch of other stuff. It's going to be at most 6. But this one wants it to be at least 7. So the alpha beta cut here says if this value is less than the alpha that I already have, then I can just return the value because nothing over here is going to matter. And look at all that stuff that I didn't have to do. So this gets a value of 6. It is not a new best value. And so the value of the root node is 7. And you can see here that I didn't have to compute this. I didn't have to compute this. I didn't have to compute any of this or this. And I got the exact same answer as if I just ran the MiniMax algorithm. So what are the computational savings of this? Well, you can see how much it's saving, and it's a lot, right? You can picture this tree being like millions and millions of nodes or something and just not having to do that. It's incredible. So in a MiniMax search tree, the number of node searched is b to the power of d. And in AlphaBeta search, the number of nodes searched is approximately 2 times the square root of b. The square root of that. So if you previously could only search to depth 7, now you could actually search to like depth 14. And so a depth 7 program in a chess game is going to be a pretty bad program, but a depth 14 program may beat the world champion, right? So the cost savings are huge. Okay. Moving on. Let's recall. So these were the 2 algorithms, right? So this was my MaxValue algorithm with AlphaBeta. This was my MinValue algorithm with AlphaBeta. And just like I turned MinValue and MaxValue into MiniMax, I can turn them into one function with AlphaBeta as well. It's starting to get a little bit long here, okay? But there you go. So it's starting to get a little bit long, but that's all you can do. Sometimes algorithms are a little bit long. But essentially, all we did is took this thing, which we already understand, and then we wrapped it around this max, right? So if I'm maximizing, do the maximizing step. If I'm minimizing, do the minimizing step. So I don't need to explain that conversion because it's the exact same conversion as with MiniMax. However, we are algorithm nerds. Can we do any better? Yeah, we can. So let's look at how we can shorten the alpha-beta pruning step on MiniMax. So down here, well, this is just the algorithm. We've looked at this already. But what I can do is I can make it a little bit inefficient. So I can make it a little bit less efficient by taking this right here and moving it up. Okay? It has the same, we will get the exact same answer. However, in some cases, it's one extra step of computation. But I'm just rearranging this, and if you analyze it, it gives you the exact same result. Okay. Now what I'm going to do is I'm going to do the following. By reordering, what it allows me to do is now compare, instead of comparing V prime to beta, V prime is also going to be stored in alpha. It's not always going to have the exact same value as alpha, but alpha's value is always going to give us more information. So I can replace this V prime and say alpha. See, just look, right above it, I'm setting the value of alpha here. If it's a new maximum, set it here. And then I'm calling that V prime. So what I can do is just use alpha, right? And now what I can do is, where I was returning V, which is this value, well, that value is now stored in alpha, right? So here I'm storing V prime in V, but now I can just return alpha, which is also storing V prime. So because I'm now I'm comparing against alpha, and I'm also returning alpha, I can actually, all this V stuff is useless because I'm using alpha as that temporary max storage variable. So all this v did was help me compute the max. So I can get rid of v. And now I deleted 2 lines of code, and now I can return v here. Okay? And what I can do instead, because I've gotten rid of this v variable, well, what I'm doing here is I have a temporary variable called v prime. The next step to shortening, I apologize if I'm going a little bit fast, but you can rewind this. The next step to shortening is I can recognize this. I'm using v prime as a temporary variable to store this min value, right? And then I'm just storing this here and then using it down here. But instead of storing a value and then comparing it, well, I could just compare its value directly by calling a min function, right? So instead of saying greater than, I could just use the max function. So now, instead of saying, okay, v prime is equal to this, if v prime is greater than alpha, alpha equals v prime. What I'm trying to say here is that alpha should be set to the maximum of the previous alpha or the new value. So I'm just going to say that. Alpha is equal to the max of the previous alpha or the new value. And then I can just delete these lines. Okay, so I have the exact same algorithm instead of, like, the exact same algorithm gives the same result, but fewer lines of code. Now watch this. This is really interesting as well. Here in this loop, if I ever have this cut, if alpha is greater than or equal to beta, return alpha. What is another way that I could return alpha here? Well, it turns out if instead of returning alpha, I just break out of this loop, well, the next line of code is also returning alpha. So if I replace this return alpha with just break, then it's the exact same thing, right? I can use break instead of return because we're returning outside of the loop. So I know this might seem like, what in the hell? Why would you do that? It turns out it's going to have a really, really good property in the next couple of slides. So we have break here, and now I have this sort of shortened version of the MaxValue algorithm. Now, what we're going to do is we apply the exact same logic, but we do it to the MinValue algorithm. Okay? I'm doing the exact same thing. So I didn't show it because I do literally the same thing, but to the MinValue algorithm. And where we were using alpha before, now we're using beta. That's it. And if you do that, you get this. Okay? But look, this over here says if beta is less than or equal to alpha, break. Well, what it used to say was return beta. Right? But before the break, I can just say break and return beta down here. But beta less than or equal to alpha, that's the same thing as saying alpha is greater than or equal to beta. So now what I have is, look at this. This line of code ends up being exactly the same. And if you ever have duplicate lines of code, then you can probably eliminate one of them. So let's keep going. Now we're going to take this and we're going to make these two min and max versions into the single long form version where we have an if statement. Okay? So what we're doing here now is we took both of these algorithms, min value and max value, we turned them into one algorithm. And so I just, like before, I put the maximizing part in here in the max, and I put the minimizing here in the max. But just look at this. Look at all these duplicate lines of code. I have a duplicate line of code here, and I have a duplicate line of code here. And really, the only difference that I'm doing here is the following. I'm maximizing over alpha. Here, I'm minimizing over beta. And here, I'm returning alpha, and here, I'm returning beta. So if I really want to be a super keener, what I can do is the following. Instead of putting all this code in the max, I can just put that if statement where I'm doing the different thing. So this becomes this. So this said for each child, I've put the maxes, the if max in here now. So if I'm maximizing, do the alpha equals max of whatever. If I'm not maximizing, then I'm minimizing. So this could just be an else, right? If I'm not maximizing, beta is the minimum of those things. If alpha is greater than or equal to beta, then break. So now you know why I wanted to put break in there. And if I'm breaking, well, when I return out, what do I want to return? Well, if I'm maximizing, I return alpha, otherwise I return beta. So this is the final shortened version of AlphaBeta. It returns the value of a state, and I'll get into that in a little bit. The result is exactly the same as the long version. Okay, so if you go back to that long version, which was like 30 lines of code, it will give you the exact same result of this. Implement whichever one you feel comfortable with. And however, I recommend starting with the long version, and there's a reason for that, which we're about to talk about. But the reason I showed you this entire derivation, okay, through all of these steps of shortening this, is because if you look online for the AlphaBeta algorithm, now you have it in the slides, so why would you look online? But I know that it's good sometimes to go out, look at other YouTube videos, get a second opinion, like get someone else explaining it. You are probably going to see something like this, okay? And if you saw this before getting this derivation, right? If you saw that version of the algorithm, and I had taught you this version of the algorithm, which had different returns, different if statements, different almost everything, you'd be like, what the hell did Dave teach us? Why was it wrong? It's not wrong. It's just different, okay? It's just written different. So hopefully you appreciate that derivation, because I had been doing MiniMax for 10 years before someone actually, stepped me through this. But here's the last part that I have to talk about. In this algorithm, all we do is calculate the value, right? So all we know is how good that move is, or how good that state is. What we really care about is which action we should do, right? Which action should I actually do here? Well, what we have to do now is change this algorithm back to a long-form algorithm so that I can actually record the action that I want to do, right? So how do I do that? Well, the first thing I'm going to do is reintroduce that temporary variable v prime. Because instead of just taking the max of something, I actually want to know when the max occurred so that I can set the best action. So that's what I'm doing here. I'm reintroducing this variable and I'm saying if max. So I went back a little bit in that derivation. So if max, I'm saying if max and v prime is greater than a, right? So now I'm back to saying if I'm maximizing and this is a better value. I'll show you why this is, but just bear with me. Now what I want to do is how do I actually know where to record the value? Well, if we go back all the way to the tree, right? We have this tree and we're doing cool stuff in the tree. It's these actions that I care about, the actions of the root node. I don't care 10 moves from now which was the best action. I don't need to record all of those actions. All I care about is which action gave me the best value at the root node. How do I know in my recursive algorithm that I'm at the root node? Well, the depth was 0. So here, I'm going to put in one extra check that if I'm maximizing and I've found a new maximum, if the depth is equal to 0, then record the best action. So if I'm saying if I'm at the root node, record the best action. And so this, we can use some sort of global or state variable to record this best action, and I'll show you how to do that for our assignment. But here is the long version of AlphaBeta, and this is what I recommend doing for the assignment. It records your action for you, okay? And there's the recording of the action right in there in the long form version. Now, in the assignment, you're going to have a time limit. I know this is going to go just a couple minutes long, I'm sorry. What if we want to have a time limit in AlphaBeta? Well, we can't just say, okay, how many depth do I think I can search in a minute or a second? Because it's going to vary based on the game. So what we're going to do is we're going to look back in the course at iterative deepening. Remember iterative deepening I talked about? We're going to do iterative deepening AlphaBeta search. And this is what you're going to be implementing for your assignment. So for depth 1, 2, 3, up to infinity, we're going to perform an AlphaBeta search to depth D. When time runs out, we're going to record or return the best action from the last fully completed depth, because we can't trust an action from a search that didn't complete. What do I mean by that? Well, if we're up here at the root node, let's say I currently have a value of 7 for this action, and maybe I'm currently evaluating these nodes down here, right? If I have to stop the search while I'm evaluating these nodes, I have no idea what the value of this node could be. It could be 1,000,000. So if I have not finished that depth of search, then I don't want to trust it. So what I'm going to do is when the time runs out, I'm going to return the best action from the last fully completed depth. Okay? So how do you actually... Okay, now you might say, well, Jesus, Dave, I'm in the middle of a recursive function. How do I actually escape from a recursive function? How do I do that? Well, it turns out it's great in JavaScript. You can just throw an exception. So you're going to throw an exception. It will unravel all the recursion for you. It'll be great. So in assignment 3, here's what you're going to do. I have essentially written down a bunch of assignment 3 for you. You are going to have a number of variables here talking about the current max depth that you're searching, the best action, the current best action, the max player, etc. And you are going to have a function, which is eval. Okay, that's the heuristic function. You're going to have iterative deepening AlphaBeta. That's a function. And you're going to have the AlphaBeta function itself. Just like in previous assignments, this is your iterative deepening AlphaBeta function. I have written it for you on the slides in pseudocode. Actually, it's almost exactly JavaScript. It's depressing how much I've done of this assignment for you. Please don't go online and copy and paste someone else's AlphaBeta, because this is the iterative deepening AlphaBeta that I want you to do. And so what it says is, okay, here's how it works. Iterative deepening AlphaBeta is going to successively call AlphaBeta with gradually increasing depths. Hopefully we get to the end of the tree. Probably we won't. So I'm going to say, okay, I currently don't know what the best action is, so I'm going to set that to null. And the maximizing player is the player that's currently to move in the state. So if I have a game of chess and the black player is going to move, then the person who's maximizing is the person controlling the black pieces. Okay? Then I'm going to have my loop that goes for depth 1 up to some maximum depth, right? And then I go for every depth. So I'm going to say, I'm going to record a class variable called current max depth, set that equal to the current value of this iterator. Then I'm going to have a try catch statement. And what we're going to do is try to solve AlphaBeta up to that given depth. If AlphaBeta completes, then we will make it to this line of code, which will set the best action accordingly. All right? So we have two values here. We have the current best action. That is the best action that the current iteration of AlphaBeta is thinking is the best action. That's being recorded. Only if AlphaBeta completes its run will this line of code be called, and then I'm going to say, okay, that level of AlphaBeta was completed, therefore I trust it, therefore record the new best action. If it wasn't completed, it's because I threw an exception. Let's call it a timeout exception. You can call this exception whatever you want. If we timed out, then as you know, hopefully, if you catch an exception, the try block, it gets removed. Like I stop executing this try block. I go straight to the catch and I skip setting the next best action. So that's how we only trust the actions from completed AlphaBeta depths. So We catch that, we break out of this loop, and we're done, and we just return the best action. So that is iterative deepening AlphaBeta. And here, this is AlphaBeta. This is the entire algorithm that you have to write. You can take this and translate it into JavaScript, and your algorithm should just work. Okay? So it says, if the state is terminal, or the depth is greater than my current max depth, which was set by iterative deepening AlphaBeta, then I should return the evaluation. So that is a terminal node. It's a leaf node in my search tree. Otherwise, if my time elapsed is greater than the current config's time, throw a timeout exception. So that's how I stop my search, is I just throw a timeout exception. Otherwise, if I'm maximizing, do the maximizing step of AlphaBeta, or if I'm minimizing, do the minimizing step of AlphaBeta. What I recommend for assignment 1 is, because AlphaBeta can be a little bit tricky, maybe implement MiniMax first. Okay, so start out by implementing MiniMax. Once you get MiniMax to work, then just put in the extra variables for AlphaBeta and see if you can get that to work. Okay, because remember, AlphaBeta is just an improvement to MiniMax. It is not a different algorithm. Here's the shortened version of AlphaBeta, so you can put this in there if you want to. However, just understand that this version is going to be a bit harder to debug than this version. Typically, it's a good rule to know that the shorter your code, the more things are happening per line, and so the harder it will be to debug, basically. And AlphaBeta is kind of difficult to debug. So, some exam questions. Know the relationship between MiniMax and Nash equilibrium. Know the MiniMax and AlphaBeta algorithms. You may be required to regurgitate them. You need to know, why is iterative deepening necessary to implement something like a time limit? Why did we need iterative deepening for that? How AlphaBeta pruning helps MiniMax. What exactly is it doing? And given a tree with leaf values, compute the MiniMax or AlphaBeta values that were returned. So that tree that I showed you, right? Let me just go back. If I give you this tree with these values, you should be able to do MiniMax on that and give me the resulting value up here at the top. You should be able to do that. Okay. So if I go really quickly, so the lecture time, okay, we didn't go that far over. That was the lecture time for this class. Okay. Now, I want to explain what's about to happen. Because of the timing of midterm break this term, look at this. I could give you assignment 3 on next Thursday. I could give you that assignment a week from now, right? And take this lecture right here to give you assignment 2, which would give you 12 days to work on assignment 3. But what I want to do is, for those of you, I know there's a bunch of people who are already done with assignment 2 and have asked, hey, assignment 2 is already done. Now, I know that's not for everybody, but what I want to do is I want to give you assignment 3 today in this lecture. So please understand, I'm not trying to give you super long lectures all of the time. In fact, I am giving you the lecture before the midterm completely off to work on assignment 3 and to study. And I can do that by so next week you have no lecture on Tuesday because it's midterm break. And then you have no lecture on Thursday because I'm giving you that lecture off, okay? But in place of this lecture, if this was switched, I could maybe give you the assignment on Tuesday, but I just want to give you as much time as possible to work on the assignment. So what I'm going to do now is I'm going to explain assignment 3 to you, okay? I'll have assignment 3 ready for you and up there tonight if you want to start working on it, rather than take a week away from you to work on assignment 3. Now, I understand that it's probably the case that none of you are going to start working on it until after the midterm anyway. I understand that. But you should work on it before the midterm because it will help you study for the midterm. So it's kind of 2 birds, 1 stone, right? By doing assignment 3, you are helping yourself understand MiniMax and AlphaBeta even more. So even though the lecture technically, the time is over, instead of just giving it to you a week from now, I want to show you assignment 3 now, right? I'm just giving it to you early. I'm taking extra time today. It might take a half an hour, 40 minutes, but I'm just giving it to you for extra time. So please don't complain about the long lecture. I am doing this for your benefit to give you extra time only if you want to. If you don't want that, then fine. Just watch the assignment part whenever you want, right? But there's nothing bad happening to you because of what I'm about to do. But all right, just wanted to explain that. So here's assignment 3. Assignment 3, we are playing Connect 4 with the MiniMax algorithm with AlphaBeta pruning. So I am giving you this interface in which you can play Connect 4. So what is Connect 4? Connect 4 is a very simple game. Hopefully you have played it before, but if you haven't, I will explain the rules for you. Connect 4 is played by 2 players. You have a blue board, this is played with a physical board. And what happens is with the physical board, you drop a piece into the top up here, and it goes all the way down until it hits another piece. Okay? So if I had a board, let me just place some stones like this. If I were to drop a piece at the top, it would come all the way down to the bottom like this. If I were to drop a piece into the top in the third column here, it would go down and then hit this piece. Okay? So it's sort of you stack pieces on top of each other, and you choose on your turn, your action choice is to take your color disk and drop it down that column. That's what happens. And it's called Connect 4 because the winner of the game is the person who connects 4 pieces of their color in a row first. So here, for example, player 2, who is placing red stones, has placed 4 pieces in a row, right? Those pieces can be horizontal, vertical, or diagonal, as long as you have 4 in a row. So let me show you an example of horizontal. So this is a win for player 1, okay? And I'm hitting reload to do this. Here we go. So I'm just showing you this is a diagonal win for player 1, all right? So the whole strategy of the game is making decisions on where to place your disks so that you're trying not only to get your pieces to go 4 in a row, but you're also trying to block your opponent from getting 4 in a row. So in the most basic example, let's say I'm yellow, my opponent is red, right? We just start placing stones like this, yellow, red. Okay, what should red do right now? Well, red, if it just tries to go for its own Connect 4, if it places it here, then yellow is just going to be able to place it here, right? On the next turn and just win. So what red should do here is place their stone on top to block yellow from being able to win. So what I have done is the following. I have created, should I explain that now? No, let me explain the user interface a bit more before I get into that. I have created a user interface in which you can select from a number of different players. Okay, so if you have human selected, then the GUI is active and you can place stuff in the GUI. If you have an AI player selected, right now it's using my solution code. If you have an AI player selected, then you can set the parameters of that AI player. So you can set the time limit, and this is in milliseconds, so 1,000 would be 1 second. If there is a time limit selected, you can also set the maximum depth. So the maximum depth, for example, 1 would look at only the next moves that I can do. So it'll only look at the next moves and not consider any of the moves from the opponent. And what happens here is that if you have, for example, both a time limit and a maximum depth selected, then the search will end at whichever comes first. So for example, if you have max depth of 1 selected, it is probably the case that your max depth will be hit before the max time limit. If I set a time limit of 0, then it will say that this means there is infinite time. There is no time limit. So if there's a time limit of 0 and a max depth of 3, that means it will search 3 moves into the future. If, however, there is a max depth of 0 and a time limit of, say, 5,000, then that means that there is no depth limit, but the time will stop it at 5,000. So if both are set, it's whichever comes first. If either of them are 0, it means there is no limit. And if both of them are 0, it means it will try and search the entire game tree to the end of the tree. And if you try and do this from the beginning of the game, there won't be nearly enough time, so you'll just hang. But if it's near the end of the game, then it might be able to search to the end of the game. So for example, if I reset this, if I set player 1 to yellow and player 2 to my solution code with a 1 second time limit, then if I click, okay, I'm playing as a human, there we go. I moved as the human. Now, nothing has happened because the other AI player hasn't gone yet. The way I tell the AI player to take a move is I can either say, hey, AI, do a single turn, and it will think for its time limit and then do 1 turn. So if I make another move, it won't do anything. If I turn on autoplay, then what happens is whenever it's an AI player's turn to move, it will move, right? So you just saw that it moved. Now I'm going to place a stone, and you'll see that the AI automatically takes its turn. I'm going to stop it from winning. Now the AI takes its turn. So that's what autoplay is. And I'm going to turn it off for a second and reset. I have 2 other players here. One is a random player. So the random player will literally just take a random action. So an action in here is just choosing one of the columns at random to place your piece in. So if I click do single turn, you'll see that this AI is just taking random actions. Okay, it's just taking random turns. If I turn on autoplay, now random player is a very quick player, so don't blink. There we go. The game is over eventually when the random players have fought. Sometimes the random players will win or lose. Sometimes they'll draw, and a draw can happen if the whole board is filled with no Connect 4. So if I restart the game, they'll start playing again, right? There you go. This other player that I've included called Greedy, all Greedy does is it does that depth 1 greedy thing. So it will say, can I win right now? If I can, I'll take the win. Otherwise, I won't. So if I have, let's reset, and I'll turn it on to Greedy, and I'll play against Greedy. So let's say Greedy is here. I'll turn on autoplay. So Greedy just places on the left side of the board unless it sees that it can win, right? So let me just do this. I'm going to try and set up a win for Greedy. So just give me a second here. I'm going to place over here, then here, then here. Okay, so there. So you saw Greedy just placed left, 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 left until it saw a win, and then it took the win. Okay, so if you see Greedy play against random and then restart the game, it's probably the case that Greedy is going to win against random, right? Because Greedy just places them on a stack until it sees that it can win, and then it'll win. So very rarely does random play against Greedy. And these random and greedy players are just there for you to be able to test your AI against. Okay? The next thing in the UI is the board slider. So it's not just a 4x7 board. This is like, it's an actual board where like you can make it as big as you want. It turns out that the game starts having some crazy properties when you make the board as big as you want, but it's there if you want to test it. So just make sure that, so after you submit your AI, we are going to have an in-class competition for Connect 4. And it's not going to affect your grades if you don't do well. It's not going to affect your grades if you don't do well. But I will devote an entire lecture at some point. Do I have a lecture here? So maybe like the Remembrance Day lecture. I'm going to take that lecture and I will live stream the entire competition for Connect 4. And so I'll do a bonus live stream. You can tune in. We did it last year. It was super fun. I had a lot of fun. I was like giving commentary and stuff. So it's interesting. But just realize that in the competition, I'm going to be resizing this board. So your players should be able to play on any size of board. Alrighty. Oops, didn't mean to open that. Okay. So the other thing here is that, so if I do a bunch of actions, sometimes it's nice to be able to undo an action. So there's an undo action button here where I can undo something that was just done. And I have also included some debugging things for you. Now, AlphaBeta is probably going to be the hardest algorithm that you've ever had to debug. So if you implement it perfectly from the get-go, congratulations. If you don't, it might be a bit of a headache to debug. It's a little bit annoying. So what I've done is I've included some test cases here. These test cases are as follows. They are different setups for different depths of look ahead for AlphaBeta. Here's the first one. Depth 1. Depth 1 is called win. The reason is that in this scenario, and by selecting depth 1, it sets all of these parameters for you. So it sets the time limit, it sets the maximum depth, it sets the AlphaBeta. So it is yellow's turn to move. So it says, with a search depth of greater than or equal to 1, but also with exactly 1, yellow should win the game immediately by placing a piece on top of the yellow stack at column 1. So this is not column 2. This is column 0, 1, 2, 3, 4, 5, 6. Okay, that's how they're labeled. So if I say do single AI turn, my solution AI will correctly place the stone on top of that column and win the game. If your AI does not do that, then it is incorrect. This is how we will be marking your AI. Okay, so these have to be correct. Here's the test for depth 2. So with a search depth greater than 2, yellow should block red from winning the game on the next turn by placing its piece on column 5. A depth 1 search will not necessarily place the piece there, since depth 1 only checks for immediate wins. Depth 2 checks opponent replies to your own moves. So what this means is, let's say, for example, I was the human player here. If I place the piece here, then on the next turn, red is going to place it here and win the game. So your AI should be able to see that. So me placing my piece, that's depth 1. The opponent placing the piece, that's depth 2. So your AI should be able to say, for every move that you can do, check what the opponent will do. And if it does check every move that I can do, it should be able to find out that every single move except this move will be a loss for me. Because on the next turn, my opponent could have put that red one down there and won the game. So for depth 2, if I do, so I've got depth 2 selected here. If I say do single AI turn, your AI, once it's complete, should place the yellow stone right there. Let's go even more complicated. Depth 3. So with a search depth greater or equal to 3, yellow should recognize that in 3 moves, it should win the game no matter what red does, as long as it places a piece to continue its current line along the bottom row. No matter where red will place its piece, it cannot win. Yellow should place its piece in column 2 or 5. A shallower search will not be able to draw this conclusion. So what does that mean? So it means that the player to currently move, if it moves here or here, it is guaranteed to win 3 moves from now. Just watch. If I place it here, now it's red's turn. Red says, oh crap. If I place it here, well then yellow can go over here. If I place it here, yellow can go over here. So if I undo that action, right, then if I hit do single AI turn, then in order to get full marks, your AI should either place it here or here to follow this logic. And it did. Okay? Let's go one more level to depth 4. Depth 4. So yellow should recognize that in 4 moves, it will lose the game if it does not immediately place a piece to either side of red's pieces on the bottom row. If both ends are left open, red can place a piece in column 2 and then win the game on its next move. A shallower search than 4 may not be able to draw this conclusion. What does this mean? Well, let's look at it. So it's currently yellow's turn to move. If yellow does not place a piece either here or here, then on the next turn, red will be able to do the opposite. Okay? So let's say I place my piece here, then red can do the same thing that we talked about last time. It can place it here or here. If it places here, then it's going to be able to win here or here. So that is something that you require a depth 4 to look at. So to get full marks, to do a single AI turn for depth 4 search, yours should block it either here or here. And so that's what the solution does. There you go. Okay. The only other thing remaining to talk about in the user interface. Oh, actually, let me see if I can show. I'll do that later. All right. So over here, the only thing left to talk about is that if I hit the print eval button, it will call your evaluation function and it will print it over here in the side. So if I set both of these to student alpha beta and then hit print eval, the evaluation function that you write will be printed over here. So you can use that to debug your evaluation function. That's what this button does. Okay, so that's what the assignment is. Let's jump into the code like we always do. So here is the code. Again, we have like 2 user interface and an HTML. You're not going to be looking at those user interface things or the HTML thing. You don't need to worry about any of that. That's already done for you. That's the user interface stuff. The first thing you should look at is this GameState class. So the GameState class has, it stores essentially a 2D array of values to store this board. Okay, so the way that this is done is it's a 2-dimensional array, and it stores whether or not, it stores one of 3 possible values. It's either going to store, if it's blank, it's going to store no piece. If it's player 1's piece, or yellow, it's going to store player 1, right? So maybe a 1. If it's player 2's piece, it's going to store a 2, something like that, right? And that's it. So that's how the board is represented. It's a board, it's a 2D array of integers. If we look over here, we can see that I have some values in here. And these are the integers that I'm going to be storing. So player 1 is going to be represented by a 0 in that board. Player 2 is going to be represented by a 1. So if we alternate moves, it's 0, 1, 0, 1, 0, 1. If there's nothing in that space, then it's going to be a 2. So that's just how I'm choosing to represent it. You could choose different numbers. And there's one more integer here, which isn't stored in the board, but the way that you are going to be able to tell if there's a winner is I have included a function which is getWinner, okay? If player 1 is the winner, it returns player 1. If player 2 is the winner, it returns player 2. If there is no winner yet, so the game is still ongoing and there has been no winner yet, it's player none because no player is winning. And the only remaining scenario is if there is a draw. So if there's a draw, and a draw can happen if the entire board is filled up and there is no winner, then it will return player draw. Okay, so that's what that additional player is that sort of didn't make sense at first. So the game state, you kind of need to know how the game state works. It's going to be constructed with a width and a height. That's pretty standard. So I'm storing the width and the height inside the board itself. It's got this dot pieces is an array, which is of length width and stores the number of pieces in every column. Okay, so if I just let's let 2 randoms play out for a second. Okay, so this dot pieces is a counter of the number of pieces in every column, which may or may not be useful to you, but I've included it there. So for example, if you called this dot pieces 0, that would be 3, because there are 3 pieces in the 0 or first column. Here it would be 4, here it would be 1, 0, 1, 1, and 2. So that is what this dot pieces stores. It's an array of length, width of the board that stores the number of pieces in each column. I've also got an integer which stores the total number of pieces on the board. That's pretty obvious, but here it would be 3, 7, 8, 9, 10, 11, 12. So this dot total pieces would be 12. This dot board, that is the array. I've set it up with some fancy JavaScript syntax here. This dot player, that is an integer representing whose turn it is to move right now. So at the beginning of the game, it is player 1's turn to move, or yellow. So that means it is this dot player would be 0, because 0 is player 1. If it was red's turn to move, that's player 2, and so this dot player would be equal to 1. Okay? So whenever a player takes a move, it alternates between 0, 1, 0, 1. This DIRS thing, that's just a helper function that I have written, which I'll explain in a second. This dot connect says how many pieces in a row do you need in order to win? And this win info is another structure that I'm using that you don't need to worry about, which I'll explain in a second. So, in order for you to get access to the board pieces, so over here in player student, just like you were given a grid before, you are going to have a board that is accessible to you, okay? And that is the state. So this game state is going to be passed into your functions. And oops, this get hash shouldn't be here. I'll fix that. So you're going to have your AlphaBeta function, or your evaluation function, is going to take in a state, and the state is this GameState object. So if you want to be able to query, hey, is there a piece, or what type of piece is on like row 5, column 3, you can use state.get, and that will just return whatever piece is on the board at that, okay? And that will be the integer associated with this. IsValid. IsValid is a nice little function. If you have an X and Y location, you are returning true for isValid, and this is done for you. The whole board is done for you. Do not worry about the board. I'm just explaining how it works. Like if I passed in isValid 2, 2, it would be this place right here. That is a valid place on the board. If I had X equal to 10, it would not be a valid place on the board because it is off of the side of the board. So this is kind of like the isOutOfBounds function. It's just saying, is this XY location a valid piece on the board? That's it. This is a doAction function. DoAction takes in an action, and the action is an integer representing the column to place the piece in. So in this assignment, your AI is trying to decide on an action to do, right? In assignment 1, an action was an XY movement in the grid. In this assignment, an action is just a choice of an integer between 0 and width minus 1. And that integer is which column do you want to place the stone in. So it's very, very easy to be intuitive about that, or to visualize what that is. Your entire algorithm is just returning a number between 0 and 6 for a board of width 7. So in order to do an action, what has to happen? Well, if I was to do action 2 here, what do I need to do? Well, I need to place the thing on the board in the correct location. I need to increase the counter of pieces on that column, and I need to increase the total number of pieces on the board. That's basically all it does. So it says it puts it into the correct place on the board. It counts the number of pieces, increases it by 1. It changes the player to move from 0 to 1. And it also increases the total players on the board. Okay? And undo action does the opposite of that. It just says, what was the last action that I did? Well, if I tell you that the last action I did was action 2, then it takes that piece off of the board and does the exact opposite of what I just did, which is remove a piece from the column, remove total pieces, and also switch the player. So do action and undo action implement the actual game mechanics for you. Is legal action checks to see if an action is legal. And the way that you do that is very simple. The only way that an action is not legal is if it's outside of the dimensions of the board, or if the column is already full. So here, the legal actions would be 0, 1, 2 is not legal, so 0, 1, 3, 4, 5, 6. So 2 is not legal, 0, 1, 3, 4, 5, 6. Those are the legal actions for this state. This function just does that for you. I won't even read the logic. Get legal actions just iterates over each possible action and returns an array of all the legal actions. So it looks over all the actions, checks to see if they're legal, and returns you the legal actions. Okay? So all that stuff is done for you, and you can just call these functions. So all you need to worry about on this assignment is your algorithm. The connect for stuff has already been done for you. This function here is winner. What you can do is if you want to know if the game is over, you can call state.winner. And state.winner, I'm not going to go through all the logic, but essentially what it does is for each place on the board, it iterates over every location and checks all the horizontals, all the verticals, and all the diagonals for 4 pieces of the same color in a row. And you can see the loop here. I won't get into it. You can look at it if you want. But it'll return player 1 if player 1 has already won the game, player 2 if player 2 has won the game. It'll return player none if the game is not over, and it'll return player draw if the game is a draw, meaning the entire board is full with no winners. Down here, I have implemented a function called copy, which will return for you a copy of the game state. This is very similar to the clone function in Java, but essentially, because AlphaBeta expects, the only way AlphaBeta works properly is if you pass things by value, right? So in order to pass things by value, you need to be able to copy a state. And if you just set a new variable in JavaScript, it won't deep copy the state. It will just have a reference to that state. So what you're going to do is you're going to use this copy function. And I'll show you how you do that in a minute. Before we get into the actual student code, which I'm going to get into at the very last of it, I'm going to show you this players function. And, the players.js. Players.js has sample functions for you that you can look at in order to do things like, hey, how do I iterate over all of the actions? Well, this function is here to allow you to look at that. So every player class has to have 2 things, a constructor and a getAction function. So if we look at the random player, remember the random player out here, all it does is select from a random legal action. So this player is very, very easy. All it does is select a random legal action. So how would we select a random legal action? Well, look at this. Let me actually make this a little bit bigger for you. The way we would select from a random legal action given a state is we can say let actions equal state.getLegalActions. And then all I have to do is return a random element from that array. And you can do that however you want. How I've chosen to do it is just say, get me a random number between 0 and actions.length, floor that, and return it. That's it. So we've gotten all of the legal actions, and we return a random one. That is the entirety of the getRandom player. Very, very simple. The greedy player is a little bit more complicated, but it will have things that you are going to want for your assignment, okay? I'll get back to this eval function in a second. But what it's going to do is it gets passed in the state, just like yours will be passed in a state. First thing it's going to do is get those legal actions, right? So it's going to say, okay, what are the legal actions? Now I'm going to say, I'm going to set up a variable, which is the current player who is to move. right? So who is the player that is moving? Record that. I'm going to try and record a maximum action. So it's greedy. It's just going to look at the result of all of the actions of me doing something and then return the best one. So it's going to record the maximum and it's going to record the maximum action. Then it's going to say, okay, now it has to implement each action that it can do at that state. So how is it going to do that? Well, I'm just going to iterate over the legal actions array. So for a equals 0, a is less than actions.length a++, that's going to be my index into my legal actions array. I'm going to copy the state. This is very important. Okay, so I copy that state. Then I do the action for that child state, right? So over here, I've chosen, okay, I want to do action 3. So I make a copy of the original state, so I don't modify the original state. Then I do the action in the copy of the state. Then I apply the evaluation function and record the value. So I say value equals this.eval. And this.eval is what's going to give me that value, and I'll get to that function in a second. If that value is greater than my current maximum value, record the value and record the action that performed the value, and then return the maximum action. Okay, so the only thing we haven't talked about is this.eval, which is looking at the board and coming up with a value. Here's how it does that. So it gets passed in a state, and it gets passed in a player. The player here is going to be the player whose point of view we want the evaluation to be from. Because, for example, if I'm winning, I want a high value. If the opponent is winning, I want a low value. So that's exactly what this does. And it's it's the most basic possible evaluator. It says, get me the winner. So look at the board, get me the winner. If the winner is the current player, return 10,000. That's a big number. It could be 1, it could be 1,000,000, but some kind of big number. So if I'm winning, that's really, really good. Otherwise, if it's a draw or if there's no winner yet, just return 0. But if none of those are true, then the other player must be winning. So if the other player is winning, return negative 10,000. So all that's saying is that if I'm winning, return 10,000. If I have won, not winning, there's no such thing as winning. If I have won, give me 10,000. If the other player won, give me negative 10,000. Otherwise, give me 0. Okay? That's what it's doing. So it's just very greedy. If it sees that it's going to win from any of these moves, it'll just do that move that'll make it win. And there you go. So there's some sample code here. When you go to generate your child states in your AlphaBeta algorithm, right? Because over here in AlphaBeta, you've got for every child, right? So instead of saying this, what you're going to do is you're going to scroll down here. You've got for C in children, right? And what you're going to do is something like this. This is you can take these 3 lines of code, copy and paste them over to your AlphaBeta, because that's exactly what you're going to be doing for that. So these are here just to show you how you get passed in a state and how you work with that state. So that being said, let's finally go look over at the player-student class, and just like all of your other assignments, this is the only thing that you're going to be working with, right? You're going to be filling out player-student. So over in the slides, I have given you all of the parameters that are going to be class variables in the player student. So again, we've got a configuration. So the configuration is going to consist of the time limit and the maximum depth. All right, so that is what the configuration is. And if we go back to the slides, we can see it's the time limit and the maximum depth. So we get passed in a config and we set that. And now we say search start time equals 0. So I've got a configuration or a variable here that records a time. And I'll get into that in a little bit, how to record time. The next variables are the best action. That's the best action we've found from the search. The current best action, that's the best action so far from this depth of AlphaBeta search. The current max depth, that is this variable here from inside the iterative deepening AlphaBeta. And this .max player, that is right here. That is the player who is currently trying to move at this state. So those are the class variables. I've put out some console.log stuff for your own benefit if you want to do that. So student to do, you may need extra variables here in order to implement iterative deepening AlphaBeta properly. So for example, you'll need to store the maximum depth of the current iteration, the best. Actually, you know what? I've already included them for you, so don't worry about that. This is a relic from a previous offering of the course where we did Zobrist hashing. It was too much for the students, so we're not going to do that. So ignore that function. Here is the function that is called by the user interface to actually get your action, okay? And so all it's doing is it's just calling iterative deepening AlphaBeta. That's it. So the get action function just calls your iterative deepening AlphaBeta function. I'll get back to the eval function at the very end. In fact, oh geez, excuse me. I'm going to put it at the very end. There we go. So here is the iterative deepening AlphaBeta function. What you are doing for this function is something like this. Copy paste over here, then turn that into JavaScript. Okay? Literally do that. It's fine. I want it to look like that. What I don't want it to look like is Wikipedia. Okay? I'm giving you permission to do this and then modify it so that it is actually working in JavaScript. Don't go to Wikipedia. Someone on assignment 1, hand it in some other website's code. I'm giving it to you. I'm giving you the code, people. All right. So the iterative deepening AlphaBeta function, what does this do? So you have to implement this function. This function should implement iterative deepening AlphaBeta. It should call the separate AlphaBeta function which implements the MiniMax search with AlphaBeta pruning. This function should use this.config.configuration options for the following. Config.timeLimit, that's the time limit in milliseconds, and a time limit of 0 means that there is no time limit. So you're going to have to put a little if statement there that says if it's 0, don't cut me off. The max depth is the maximum depth for iterative deepening AlphaBeta, and we're checking to see if the current depth is greater than the maximum depth. And the maximum depth of 0 means there's no max. So you got a little bit of an if statement there as well. You can assume that one of time limit or max depth will always be greater than 0. Okay? So I'm never going to expect you to like search the entire tree. That's what that's saying. One of them will always be 0. Please note that both of these limits should be used, and whichever happens first should do the stopping condition. So the arguments, be sure to return the best action from the last completed AlphaBeta search. We already talked about that. So the arguments are the state, that's the state for which to do the best action, and the action is what you're returning. That is the action for the player to move. And remember, the action is the column starting at 0 where you want to place the stone. So that's it. That's what you have to do. And the other thing that you need to know, that in order to record the time in milliseconds for JavaScript, you can just say performance.now. So performance.now will be the current time in milliseconds, I believe. If it's not, just go look it up. And you can say, okay, when I start my iterative deepening AlphaBeta, this .search start time equals performance.now. And that records, for example, 5 p.m. and 2 seconds and 30 milliseconds. And then you have to put your code in here. That's iterative deepening AlphaBeta. It's probably the easiest part of the assignment. The next part you have to do is the actual AlphaBeta function. Okay? Now, inside AlphaBeta, if you want to know how much time has elapsed, you say time.elapsed, or you can have this, this is supposed to be let. Elapsed time is equal to performance.now, so I'm calling performance.now again. and subtracting when I started the search. And that will give me the amount of time that has happened since I started the search, the amount of time that has passed since I started the search, and you can throw an error if that time has passed. So, what does this say? The AlphaBeta function. This function should implement MiniMax with AlphaBeta pruning. It is recommended to first get vanilla MiniMax search working properly before implementing the AlphaBeta pruning enhancement. Please be aware that this function does not return an action. It returns a state value. Actions must be set to a self variable rather than return. I'll say that class member variable rather than return. It is important that you copy states before generating children. Otherwise, you will be modifying references to the original state on different levels of the recursion. There is a fun optimization that you can do that doesn't require copying. I'm leaving that for you to figure it out. So, optimization alert. Once you get everything working and you want your code to run faster, you will probably see that your code is running a bit slow. The reason for that is that copying the entire board state every time is relatively slow, right? Every time I go down a depth, I have to copy the entire board state. There's an optimization that you can do that allows you to not copy states. However, I want you to try and figure that out on your own. All of the code that you need in order to do that implementation has already been, it's already here for you somewhere hidden in this assignment. However, only do that after you've gotten full marks. Okay? Then try and work on this. So the arguments, of course, as we talked about, the current state, the values of alpha, beta, the current depth, and whether or not we are maximizing. Those are the values that we showed in the slides. We don't need to talk about those again. And it returns a value of the state. Could be, I say int, but it's a number. So I just reiterated for you here, be sure to copy the state before doing an action and recursing. And one of the first things that you can do here is go over to players.js, take this code, copy and paste it, and then put it over here, and then start modifying this so that it looks like this. Okay? So that's what I recommend doing, and that's why I put it there for you. Do not start by copying and pasting code from Wikipedia. Copy it from what I've already given you. Okay? Then I can help you better with the code. And then we return the value, and these return values are here within AlphaBeta. Now, the last thing that you have to do is the eval function. And let me talk a bit about the eval function. So the eval function, I'm going to turn on 2 human players. Here's the eval function. Given that the board looks like this, a good evaluation function should compute something that, for example, if it's a higher number, I want to be in this state. If it's a lower number, I don't want to be in this state. That's actually a tricky thing to do. So let's talk about the 2 extremes, right? So the 2 extremes are this case. So for yellow, this is 10,000. Let's just say that 10,000 is our infinity. Let's just work with that, okay? So I'm going to give this a value of 10,000 because it's the best possible state for me because I won the game, right? But for red, this is the worst possible state because red has lost the game. So let's give that a value of negative 10,000. Those are EO. And also, if it's a draw, the value is just 0. You have not won, you have not lost. There is no possibility of winning or losing, so it's just a 0. So, if you're in a state that's not winning or losing, how do you know how good that state is? Well, in this function, what I've done for you is I've said, okay, if the winner is the player, return 10,000, some big number. If the winner is the other player, return negative 10,000. It's really bad that we lost. It's really good that we won. If it's a draw, return 0. However, if the game is not over yet, you have to do something clever here. What is clever? I don't know. You have to come up with a function, because otherwise what you're going to be doing is what essentially the greedy player is doing, right? So the greedy player, if it's not immediately winning or losing, it just places it on the left. Because if it's not an immediate win or loss, it's a 0. And so what does it do? It just takes the first 0, right? And that kind of sucks. It would want, hopefully, maybe, okay, here's an evaluation function, a possible one. Maybe if I have more pieces near the middle, the number is higher. That's an example of an evaluation function. In chess, an evaluation function that humans often use is to say, I'm going to give a value to pieces on the board. Pawns are worth 1, queen is worth 9, rook is worth 5, whatever. I'll sum up the value of the pieces on the board, and my evaluation function is my value minus your value. So if I have more players, it's a higher number than if you have more pieces, right? It's a decent guess, but it's not perfect. But that's what a heuristic is. It's a guess at how good the state is. Let's look at one evaluation function that I'm actually going to recommend that you try to do for this assignment, because it's very powerful. This is a very powerful evaluation function. There's a concept in the game of how many places do I still have available where I could possibly make a connect for, right? So for example, if the board is empty and I'm playing as yellow, I could make a connect for here, 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 here. Okay, you can get it. I could make one here, or here, or here, or here. So let's make a function that counts the number of places where I could still make a connect for. The idea is that if I have more places left where I could make a connect for than you have places left where you could make a connect for, then I'm probably winning. It's a relatively simple but powerful evaluation function. And here's why. Watch this. Ideally, you want to control the middle of a connect for board. Why? Watch this. If I place a single piece right here, it has cut off this connect for yellow, this connect for yellow, this connect for yellow, and this connect for yellow, and this one, and this one, and this one, all by placing a single piece. If I had instead placed my piece over here for red, then the only places I've cut off yellow are here, here, and here, right? So which one of those moves would you prefer to do? The one that cut off like 10 places for yellow to go, or the one that cut off 3 places for yellow to go? So that is an idea at a heuristic function that you can do. And I will tell you that there are marks associated with that heuristic function. I'll go over the marks in a second. But in order to win the competition, you are going to have to come up with some sort of smart heuristic function. Otherwise, you'll just be placing them all the way down the left. Then, it won't be very smart. So let's go back. This is where you put, this is where you put that logic, okay? So this is where you say, okay, GameState.get x, y, I'm gonna be checking, gonna be iterating, seeing where I can make connect fors, all that kind of stuff. You can go online. I don't want you to copy and paste anyone's evaluation function, but if you go online and you find someone who talks about a really powerful connect for evaluation function, please put a comment here. I got this idea from this YouTube video, and put it in there. It's fine. Don't copy and paste their code, please. Implement it yourself, but cite where you got the idea from, and I will be okay with you getting ideas. If you put something there that I recognize from a website or a YouTube video, and I've seen a lot of them, if you don't cite it there, that will be plagiarism. But if you do cite it, it will be okay. The very last thing I will show you is the marking scheme for this assignment. So that's it. That's the assignment. It's really not that much work, but it might be a lot of debugging. So start it whenever you can. We have the standard code style readability. 10% is on your heuristic function. Okay, 10% of your assignment is your heuristic function, so please do something intelligent, and I mean something more than just counting the pieces on the board. So try to implement what I said. Okay, 10% if you get that, and anything extra is good for you. Iterative deepening alpha beta is 30%, so if you properly set the current max depth, properly update the action of the completed searches, and it passes all 4 tests, okay? Alpha beta code working properly, this is no longer a thing. So this iterative deepening alpha beta passes all 4 tests. This is also part of the alpha beta, right? You have to pass all of those tests to get full marks. And if you want to participate, so for example, if you don't get the time limit working properly, but you get the max depth working properly, you will still get some marks, just not all the marks. But to participate in the class competition and get the bragging rights, you must have both of these working properly. Okay? So just keep that in mind. What I recommend very heavily is make heavy use of the debugging options within, one second here. So for example, in my depth 1 win over here, when I click do single AI turn, you can see over on the right, I'll make this bigger, 1 second. Yes, okay, you can see that, great. So if I click, I can't click the button, all right. So here in the button, my solution code uses that evaluation function of being 10,000 for a win or negative 10,000 for a loss. So in this case, let's think about what all of our evaluations should be. If I place a stone right here, there is no win, so it should be a 0. If I place it here, I'm winning, so it's 10,000. If I place anything over here, then it's a 0, right? And that's what I see over here. So in my AlphaBeta function, in my solution, what I have done is detect, am I at the root node? If I am at the root node, then print out my values of my AlphaBeta return. Because that will help me debug and say, okay, it didn't see a win here, it did see a win here, it didn't see a win here. My best action value was 10,000 and my best action was 1. So if I then click, do the turn, that's what prints out. If I then look at depth 2, okay, and I do single A, well, let's look at this. If I'm searching to depth 2, if I place it here, well then my opponent, if I place it anywhere but right here, my opponent can win. So what I should see is negative 10,000 everywhere except right here, which should be a 0 because it's not the end of the game. So if I hit do single AI turn, that's exactly what I see. Is on action 5, that would have been a loss if I had put it anywhere else. See this? All my other actions are negative 10,000, but action 5 is 0. So the best action value was 0 and the best action was 5. So I recommend making judicious use of similar debugging for your alpha beta because it can be a little spicy to debug. Perfect. That is assignment 3. Thank you for sticking along with it. As I said, you didn't have to watch this right now, but it's out there for you if you want to start early. So that's it. Keep in mind that there is an overlap between right now and the due date of assignment 2. Assignment 2 is not due until 5 days from now. 5 days from now, which is Tuesday. So even though assignment 3 has been released, assignment 2 is not due just yet. There's a little bit of overlap just to give people as much time as possible to work on assignment 3 if they want to. Taken up enough of your time today. Thank you so much. And I actually won't see you next week. I will see you at the midterm. What I might do, maybe I'll do I'll post on D2L. Maybe we'll have a midterm study session or something like that where I can help you with some questions that you have. But anyway, have a great weekend and I'll see you next time.